So thanks very much for making it at 5 o'clock. I know it's not the last session of the day, but thanks anyway for coming to this. I've got a number of slides and some demos. We want to make this as exciting as possible. Initially, this room would host like 300 people or so. We'll see how it goes. Happy to take questions as we go along. If we start running short of time, I'm going to have to push the questions back till the end of the session. I'm happy to stay for as long as possible, as long as you need outside. Happy to answer as many questions as you like. I've been working with Parallel Data Warehouse now for easily the past 2-3 years when we first released it. Been at Microsoft for the best part of almost 20 years. Working with databases pretty much ever since the beginning when we first ported SQL Server from OS2, the old OS2 days, over to the Windows NT platform. So today we're going to talk about big data and Parallel Data Warehouse. What's Microsoft doing in this space? How do we integrate with Hadoop, the wild world of big data? So here's the agenda. Firstly, what is big data? It's pretty much if you're a data guy, you mention big data, you're instantly the kind of coolest guy in the room. Everyone wants to talk about big data. The other one is like Hadoop and Hadoop integration. There's a big movement on what it is it, how do we integrate with it, what are some of the terms that people keep throwing around. Do I have big data? That's something you guys need to figure out, and hopefully by the end of this session you'll have a much better idea. Whether you have big data, whether you want to jump into big data, what you want to do with big data. A Hadoop intro, we can talk about Hadoop for the next couple of days, but this is a very, very quick kind of intro. And also PDW. Very few people have had even know what Parallel Data Warehouse is, that we have an offering in the massively parallel space for enterprise data warehousing, i.e. Issuing a query across many, many different nodes, executing in parallel, coalescing results back, massively parallel, shared nothing kind of architecture. And we're going to delve into some of the intricacies of how we integrate with Hadoop. We'll go through some demos and pretty much wrap up and take some questions. Key takeaways from this session. What are you going to get out of it? You want to understand some of the new concepts and definitions around big data, understand how we can get some value out of big data, and leverage your existing strengths. And this is a key point, leveraging your existing strengths. So I don't know how many of you guys are SQL guys, right, and dream SQL every night, T-SQL and write queries. Well, essentially, you don't want to throw all that away. And for companies, you've got code bases and schemas and designs and design patterns. You don't want to throw all that away. You want to be able to leverage that in this new world, be able to query unstructured data and structured data, relational data, merge the two together to get a result fast. And lastly, we're going to show you how easy it is to integrate Parallel Data Warehouse and Hadoop, to be able to extract data out of Hadoop sources into PDW and be able to export data out of PDW back into Hadoop. So merging the two worlds. So largely, we're going to skip over, fairly quickly a number of definitions, kind of get into the rhythm, if you like. So what is big data? Wikipedia defines this as such a large amount of information that normal database technologies that you knew and loved and used before, it's kind of mind-boggling to be able to load all this data, process all this data. So if you were around in the keynote yesterday when they were talking about blink and you'll miss it, and an analogy in the big data space is blink and you got another terabyte of data. Blink again and your data just doubled in size. That's what we're kind of talking about in this space. So where does all this data come from? Going back, I remember quoting to customers about large databases about 10 years ago. A large database 10 years ago was, a terabyte in size or 100 gigabytes. Now you can run a 100 gig database on a laptop pretty much. You know, back in those days, in order to run a terabyte database, you'd have thousands of 2 gig SCSI drives and a room full of SANs. Now it's a lot simpler. So big data is characterized by 3 key attributes. We're talking about volume, i.e. the amount of data that we're talking about here, capturing it either in logs or getting data out of statistics, crime statistics, video information, masses of data. I was regularly talking with some of the miners, and when they do geographic analysis and mining analysis of where they're going to drill. So when they talk about big data, they talk about it in the size of pallets. How many pallets of data are we talking about from a drill site? And when I say a pallet, it's, you know, the DLT tapes, each one holding for about anything from 100 gig up to about 500 gig of data. Well, imagine a pallet of that, about stacked yay high. What a forklift can lift is basically a pallet of data. And they measure data by the pallet load. Now, we also have the variety. Totally different data, XML data, voice data, audio, video, lots of different information, RFID data, and the velocity. So from one location in one time, you got 200 different feeds. I was talking to one of the health departments. Through a change of government and change of policy, this number of feeds increased from 200 to about 400, because now you have a plethora of different, both SSIS packages, Informatica packages, data coming at you from all different directions. So, looking at big data, initially it was how fast people can type into computers. So we started off with ERP and CRM systems. Going back in the day with SAP systems, it's how many transactions you could process, and doing the payroll and the inventory. Then with Web 2.0, it started to analyze web logs, and we saw some of the digital exhaust being processed in order to get information out of it and get insight. And then the petabytes of data really come from both clickstream analysis, analyzing wikis and blogs, sentiment analysis, Twitter analysis, Facebook analysis, massive copies of data, mining data that I was talking to you about before, and even analyzing audio and video type data. Now, still, this industry is still in its infancy, realistically. And when we say, you know, analyzing non-text formats in Hadoop and other technologies, you still have to write the import functions, right? Very non-trivial. So Hadoop in this instance is really about processing log files. You know, it's you copy it into this system and you can read it in. Okay, so why should I care about all this big data? Well, we're going from an environment where in the past we were analyzing moderate amounts of data and trying to put together a data mining model. This first started with data mining anywhere for about 7 to 9 or 10 years ago. And then you train this model on some data that you know the expected outcome. And then you apply this to some unknown data. You want to get from known knowns, i.e. the data that you know the expected outcome, to some known unknowns. And I give you an example. So this is an age-old example where one of the supermarkets discovered that if you put diapers close to beer, you end up selling a lot more beer, right? Now, if you're the store manager, you wouldn't quite figure that out. But if they did the analysis on some of the stores, in hindsight, it makes perfect sense. It's 11 o'clock at night. The wife says, we're out of diapers. Okay, go off and get some more diapers. So the guy goes off to the supermarket. Now in the US, in the supermarkets, they sell beer as well. And so when you're there, it's okay. You can pick up a six-pack, and no one's going to, your wife is not going to say, hey, why'd you bring beer home? Because you also brought the diapers home. So it kind of made sense, right? But now we're in a world we want to discover the unknown unknowns. And an example of this that was discovered was, for example, in the Los Angeles Police Department. They went through and used some social engineering and discovered that there was a pattern between crime, the location of crime, and the way that human beings interact. So they took the tribes, in the Serengeti, for example, and how different tribes interact and where people interact. And we discovered that they have similar-ish social patterns. So they ran an experiment where normally the police officers drive around in their cruise cars and they have gumption and they know typically where crime is going to be. So they segregated a number of officers and they said, okay, you're going to follow a computer program. So the computer program is going to spit out different geographic locations, GPS coordinates, and you have to drive around there for the day, And the point is, if you obviously see something going on, you arrest the guy, and kind of we go from there. They discovered that we're able to correlate, and in these specific areas where crime happens, there's a secondary crime about to happen in a fairly short period of time, between 1 to 2 weeks. They were able to tie this together. So, in so doing, discovered an unknown unknown. So they were able to lower the crime by 13% across the city of LA. So big improvements in safety through essentially just mining some of the data. So some examples of big data. Now, a lot of the times, this information either gets thrown out or we put it on pallets of tapes and don't have enough time to load it, let alone process it. In a lot of cases, when you're starting to process this data, you really don't know what you're looking for. And the power of both PDW or even some of the other systems is how fast, how many queries you can run in order to try and discover patterns in unknown amounts of data. It's akin to you're looking for a black cat in a black room, and all you have is a laser pointer. And you flash it around and you whack it around as fast as you can, and hopefully you'll see a glimmer of the reflection from the cat's eyes, and you say, hey, maybe I've got something here. And if not, you go to the next room and rinse and repeat. So some of the things like the A380 airplane, each engine, 20 terabytes of data per hour. In a long-haul flight, you get over half a petabyte of data out of these systems. Now, a lot of this data is thrown out. But if you can find the 0.001%, there's new discoveries there. RFID data. In 2005, we had 1.3 billion tags. 2011, this increased to 30 billion tags. In 2014, the market is expected to quadruple, as well as the people using mobile phones and devices. All of these devices exude massive amounts of data. Even cars today. Today, cars, we don't capture all this data, but a lot of information is generated from modern-day cars. Like the M3, for example, from BMW, generates massive amounts of data. Okay, Progressive Insurance in the US has a little dongle. You can plug it into your car, and it can get your driving habits. And if you fall within certain guidelines, you get a discount. And finally, smart meters. And this is very, very close to home. Very recently, i.e. in the last 2 years, customers and the government has told utility companies that they have to start implementing smart meters. And they've gone from 1 read per month, or 1 read every couple of months in some cases, to 1 read every 15 minutes. That's massive amounts of data. I know that they were struggling getting all this data into the SAP system and being able to process it. In some cases, they've lost millions of dollars being able to run the reports in order to create the bills and get the data out. So I want to introduce the Hadoop ecosystem. And around it, some of the components where Microsoft integrates. And this, think of it as HD Insight on premise. So in this case, you know, there are some terms. I'm not sure if you are familiar at all with Hadoop or played with Hadoop or read anything about it, but it's quite a different world. It's all based on Java. So at the core of it, we have what they call HDFS, which is a Hadoop distributed file system. On top of that, there is MapReduce, which is a technology that can effectively take large amounts of data, and you can run queries on top of that and process that data. Now, on top of that, there are a number of, this is all open source, by the way, based on the Apache Hadoop standard. There's a number of different plugins and components, like Hive, if you want to write SQL-ish type queries. There is Pig, stands for Pig Latin, to be able to write kind of batch jobs. So think of Java or MapReduce as the assembler kind of language. It's very tedious, very detailed, but it gives you a lot more flexibility. I'm just giving you an introduction here. And then around that, you have other things like Flume to be able to import data, and Oozie, and HCatalog, and it's a whole different world. So Microsoft is working with Hortonworks, and I'll discuss that a little bit later, and bringing the Hadoop implementation on the Microsoft platform, either HD Insight in the cloud or HD Insight on premise. Leveraging Active Directory to be able to apply security, leveraging System Center to be able to manage this, because if you're talking about, I want to have a 200-node Hadoop implementation, management now becomes a real issue. And then finally, we want to talk about PDW, which is really the core of today's session and how we integrate with Hadoop. So one thing that we're hearing loud and clear from all of our customers is we want to be able to leverage both the power of Hadoop and the power of PDW together and be able to get data out of Hadoop in a normal SQL Server way. We've got all this code that we've written over on SQL Server. We have many programmers and coders on SQL Server. We want to be able to use the same methodologies and the same tools. We've already got Office. We've got all the entire stack. We've got a whole bunch of third-party tools that connect to SQL Server. We want to be able to leverage that rather than have to either invent new tools from scratch, make new acquisitions. So what's Microsoft doing? So a number of years ago, we first released Parallel Data Warehouse using the SQL Server 2008 platform. That was version 1. So in the past 12 months or so, we've released PDW 2012, or V2. This is far more scalable, much more powerful, and performant, et cetera, et cetera. And I'll go through into the architecture of that. And we introduce a concept called external tables. HD Insight is a 100% compatible implementation of Hadoop on the Microsoft platform, and there's a dev preview right now. So you can go through, if you are using Azure, you can implement very easily a 4-node cluster, literally in 20 minutes. You go through, you answer, I think, 4 little questions. One is the login name, the other one's the password. You have to pick Eastern Europe for where you want the storage to be located. You hit enter and go for a cup of coffee. That's it. Because normally to set up Hadoop, it's quite an involved process if anyone has done that. So that's the minimum. We can also go up to 32-node clusters on Hadoop under some of the advanced options, and it takes just as long to create, about 10, 20 minutes or so. Power BI works with this stack. You can get data out of Hadoop. Also, Hortonworks and Microsoft have been working together for quite some time to bring this to fruition. Hortonworks, the company came about because there were about a number of folks from Yahoo who built some of the first reference models within Yahoo in order to process log files. And about 24 guys kind of left Yahoo, created their own company. They called it Hortonworks, and started releasing a build of Hadoop on their own platform, be it Linux. So we're working with these guys, and we have produced together HDP on Windows, and we've also got HDP on Linux, and we're also supporting Cloudera's Linux implementation of Hadoop as well. So, PDW. A couple of slides on PDW. What is PDW? It is a massively parallel data warehouse solution. It's scale out. It's also an appliance. So when you purchase this, you don't need to install it. It's not like, okay, go out and buy a bunch of servers, buy some InfiniBand cards, and here's a white paper. Okay, off you go, build it. It comes pre-installed, pre-configured. On day one, you roll it into your data center, and you're good to go to start loading data into this. When we're loading data into this, it loads it at really high rates because we implement InfiniBand. We implement under the covers distributed processing and loading onto n compute nodes. When we're executing queries, all the queries are executing in parallel across multiple machines under the covers. Scales from terabytes to petabytes. Start small and grow as you need. Compression and updated column store technology is built in from the ground up. Not even SQL Server 2012 has updatable column store technology. So normally you got to load the data in, then you build the column store. With PDW, you don't need to do that. You just load the data in, it's updatable column store automatically. So we also provide easy Hadoop integration. So if you have a Hadoop cluster, we'll show you in this demo, we'll connect up. I'll show you the syntax. The syntax is fairly simple. I want to go through some of the details with you, and we'll go through a demo. And, of course, all of this works with the existing stack that you've got. Excel, Power BI, SSIS, SSRS, that you're potentially all very familiar with already. Your existing reports can leverage this technology. So, this is the V1 reference of Parallel Data Warehouse. We've made quite a lot of changes between the two systems. Initially, we were using fiber channel for the disk subsystems and quite expensive SANs. In PDW V2, we're leveraging the power of Windows Server 2012. We're leveraging JBOD disks under the covers. We're leveraging the new features of Hyper-V. Dramatic improvements in performance for a substantially lower capital expense costs. So essentially, think of it as large enterprise systems, Teradata systems. This is the kind of thing that we're talking about right now. So how does this work? I want to go through a couple of slides into some of the key design attributes of the architecture. So as I said before, at a base unit, it's called a scale unit. The smallest unit comes in a quarter rack. And this is kind of what it looks like. So in the smallest configuration, you get 2 compute nodes. Each one of these is connected directly via SAS to the JBOD, which stands for just a bunch of disks. We use Windows functionality built into Windows as far as providing the high availability of the disk subsystem and also for the cluster itself. We have a host for redundancy, so if any one of the hosts dies or has a failure, it automatically fails over to the redundant node. So when you want to scale out, you're basically just adding blocks of repeatable blocks of this configuration. And this is all done as part of the supported mechanism, and it's a very quick configuration because it's all come and delivered by the hardware vendor. So it scales, and this is a very small kind of detailed table, but I just wanted to include it here. I know you can download the slides and have a look at it. So there are some minor differences between HP and Dell. There are other vendors that are also coming on board as well, being able to offer parallel data warehouse. So in a base configuration under a HP, there is 2 compute nodes. In a base configuration, a quarter rack system for Dell, there's 3 compute nodes. And we basically scale from there. What's a quarter rack, a half rack, 3/4 rack, a full rack, all the way up to 7 racks. And you can see that the amount of redundancy that there is. So each rack has its own spare node. Think of it that way. So availability is built into the system, both at rack level, and you can also have situations where if all of the spare capacity, spare nodes on a particular rack has been used up, it'll fail over to one of the other racks. Now, the underlying configuration, what's holding this together from a performance perspective, is InfiniBand. We're using the very latest InfiniBand technology. And you can see how we're scaling from a small system, so you can start small, right up to over 6 petabytes in size. And this will grow over time. So, query processing, how does that work? We're talking about a scaled out, shared nothing configuration. So if you're familiar with the Hadoop kind of story and how and some of the nomenclature that Hadoop uses, they use a concept called a name node. The name node in Hadoop basically knows where all the bits of the different files are. So when you load a file into HDFS, the file is chunked up into 64 megabyte chunks. And that could be distributed from 1 to n different servers, and high availability is built in. So in the same way, the control node, and specifically the shell DB, knows exactly where all the data is, and we in fact keep metadata about the statistics, so we know the size of the data on each one of the nodes. We know the type of data that's there. Just when I say statistics, think of normal SQL Server type statistics, which are actually quite detailed. We have a very detailed histogram. Why do we need all this? So when we first execute the query against the control node, what happens under the covers? There's a process called the data movement service. So the data movement service is responsible for essentially striping out all the data where it needs to be. And then finally, helping the engine put together the query plan. We have a number of 2 query plans, a distributed query plan and an individual node query plan that executes on the SMP node. So the whole point of the DMS is to minimize data movement. Because let's face it, if you have to do a job, it's always going to be slower than not having to do that piece of work, no matter how fast you can do it. So if you don't have to move data between nodes, even though you're using InfiniBand, that's the optimizations. So what happens is that we create a D-SQL plan, or distributed SQL plan, using the data in the control node in the shell DB. So we know the metadata for all the tables, where the data is located, the statistics of the data, if there's any indexes that we can leverage or not, et cetera, et cetera. From there, we go through and we inject to each particular node in the same way Hadoop does kind of, we kick off jobs and the query is executed. Now, all this is handled under the covers. All you do is execute a query in the same exact way as if you were connecting to an SMP configuration of SQL Server, like a fast track box or SQL Server on your laptop, and just executing a query. Except from what we see, the queries that typically get executed against PDW range in the 5 to 10 pages per query. SQL text, massive queries, lots and lots of complexity, because we're not dealing with one machine anymore. We're dealing with a massively parallel solution. So a couple of points I want to get across, because these are kind of the fundamentals of being able to understand parallel data warehouse and how the system works. So we make a choice between what tables are going to be replicated between nodes and what tables are going to be distributed between all the different nodes. Replicated tables are essentially copied to all the different nodes. So think of those as your smaller tables, your dimension tables, and there's a number of rules around that. And logic, we would work with you to make that determination, or you read the documentation and you can understand that. Then, the fact tables, typically, or the really large tables, would be distributed, or think of it as striped across the different nodes of the appliance. And the DMS service takes care of striping the data appropriately, and we use certain rules under the covers so we know where the data is. And what we want to achieve is data locality. So when you execute a query, we don't want to be moving data from node 1 to node 2, or this is called a shuffle, essentially. We don't want to be shuffling the data between the nodes. We want all the data to be local. So when we're executing the query, we're actually firing off a number of queries per node, and in fact, one per distribution. So we could be firing n number of queries against all of the nodes, coalescing all of the results, and streaming those back to the client. So under the covers, when you create a distributed table, what does it look like? You have distribution, in this case, create table, my table. This is a little bit of new syntax in PDW with, and you label the distribution hash on a particular column, in this case called ID. What happens under the covers? We are creating 8 tables per node, or 8 distributions per node. So on a one rack system, say from HP, that has 8 nodes, it would be 64 different nodes, distributions. So when we execute the queries, we're actually firing off 64 different queries at the same time against the system to execute part of this query. Then we roll up these results, and this becomes part of the distributed execution plan. So I can show you a distributed execution plan during the demo. So Microsoft, a number of years ago, out of the Jim Gray labs, put together a project called Polybase, called Project Polybase, with SQL PDW 2012. So some of these design goals will show you the power and the foresight and what we're thinking and where we want to take this. We want to achieve seamless querying of both non-relational and relational data together. So you can write normal SQL, and whether it's relational data or non-relational data, you can join it. You can have the data in PDW. You can have the data in Hadoop. You can mix and match. You also want to improve performance. So I talked about Scoop, and there are a number of data connectors. One of them between Hadoop and the rest of the world is Scoop. What is Scoop? Literally, it is scoop some data out of Hadoop and put it into a relational system, or scoop some data out of a relational system and put it into Hadoop. That's literally the definition of the name. But the problem is it's serial. So it's how fast can you get one thread to either read or write, and that's typically measured in a couple of gigabytes, X gigabytes per hour. That doesn't really scale when you're talking about a massively parallel system. So we wanted to make this parallelized. Parallelized data import and parallelized data output back into Hadoop, being able to transfer data at a really high rate of knots. And we'll show you this in a little while. So we also wanted to support current and new implementations of the Hadoop platform. So this is currently, we support HTTP on Windows Server. This is the Hortonworks implementation, or Hortonworks HTTP on Linux, as well as Cloudera's HD4, which is based on Hadoop kind of 2.0. And all of these are 100%, Apache Hadoop compliant implementations that you can build large farms with. So Polybase, we're using and enhancing the data movement service to be able to understand external data and external tables. Why? Because data scientists don't really care where the data is. You just want to be able to query it. whether it's in Hadoop, whether it's audio, video data, or text-delimited data. You just want to be able to query that and produce your reports and make sense of the data. So through the enhancements of the query engine, the external table references, and the HDFS bridge, we're able to produce all this. So from the control node to the compute nodes, we talked about the distributed execution plan that we're then cutting up and we're sending it to each one of the compute nodes. Each one of those compute nodes instantiates a number of threads, one per distribution, and is able to, in parallel, per compute node, be able to bring in data from Hadoop and be able to output data to Hadoop as required by the query. So we're analyzing the query. So let's have a look at some of the syntax under the covers. So in this case here, what do we have? We have create external table. This is new syntax. Obviously, we give it a table name. And the table name is nothing but a reference. Think of it as a shortcut or a link. We have a number of column definitions. Why do we have column definitions? Well, remembering that Hadoop typically is a schema on read rather than schema on write. Normal relational systems is schema on write. What do I mean about schema on write? If you're going to write data or load data into a database, what do you need to have? You need to have a table. Well, what is a table? It's a container where the schema has already been defined. The first column is an integer, the second column is a date time, et cetera, et cetera. When you load data into Hadoop, you don't have any of this. It's essentially a file copy. All right, a little bit more to it than that, but essentially you're chunking it up into 64 megabyte chunks and kind of throwing it around. But it's a big copy. It doesn't even go to the point of going to the end of a row. It chops rows halfway through as you put it out in 64 megabyte chunks. So here we're defining the data as we're reading it. So you still have to do the work. It's just that when you do it. In a database, in a normal database load, you've created the types. When you load the data in, if you're trying to put a varchar in a date time field or a number in a date time field, it'll fail. Well, in Hadoop, you just load the data in, but when you read it, that's when you have the problem. So you still have to handle the situation. So we also have the format options, and the format options are defined as such. We have the field delimiters, field terminators, the string delimiters, like I want to put quotes around all my strings or not. The date formats, whether it's DD, MMYY, or MMDDYY, that kind of thing. Remembering right now, you have to define all this before you start reading in the data, or as you're reading in the data, because you're actually just reading in a text file. It's a text file. It's not a table. It looks like a table. It feels like a table, but it's not a table. It's just a text file. So we also have reject sample values. What do we do with the data that doesn't make it? If we have gobbledygook data, your RFID scanner went crazy one day and it recorded gobbledygook where it should have recorded real data. What do you want to do with that? Do you want to fail the load? Do you want to ignore it? So on and so forth. So we have the concept of external tables. And we've implemented this via a HDFS bridge within the Data Movement Service, or DMS. And what happens is the HDFS bridge is comprised of C# calling Java APIs, Java HDFS APIs. So we talk directly to HDFS via the name node. So when we go through and create this or read the data from Hadoop, we go to the name node. We discover where all the blocks are, the 64 megabyte blocks are, and we start going to those individual servers and start reading in the data from there. So then finally the HDFS bridge, obviously using C#, interacts with the DMS service. And the DMS service then is the internals of PDW, and then that distributes the data evenly across all the compute nodes within Parallel Data Warehouse. So what's the architecture look like? You execute create external table statement. What happens? Well, under the covers, we parse that. We take the path to the file. We determine, can we open the file? Do we have permissions to open the file? You create a PDW user in HDFS so that you can access the data. Then we take some statistics, the size of the file that we're talking about, the number of rows, the length of each field. This comes in very handy later on as we're making a determination on how we're going to process each query. Then this is called essentially file binding on the split and splitting the data as we're writing it out back into Hadoop. And then we parse the format options needed for import. And that's basically it. We write all this metadata then about the location of the file format options, what we've got and where it is back into the control node. So as a summary, for the external tables, think of it as links to external systems. Now in this case, we're talking to Hadoop. In the future, we're also adding extra functionality in this space. So watch this space. So right now, there's no data actually stored in Parallel Data Warehouse when you create this external table link. Of course, you can use that to bring data in or put data back out to Hadoop. So let's see if we can connect to our demo. I just want to run a very quick demo over here. Okay. So this is my appliance. I've opened up Visual Studio Data Tools, and this is a free download. If you've got Visual Studio, you can install all of this very easily. So this is my Parallel Data Warehouse connection. I'm using this IP address and the port 17,001. So as opposed to 1433, which is the default port for SQL Server, it's 17,001. So we're making this connection. So I'm using a database called TechEd 2013. So use this database. So we execute this. And then let's go through and let's make sure that I don't have any external tables. I can have a look at my databases, system tables, what system tables I have, external tables, and normal tables. So this right here is a normal Parallel Data Warehouse replicated table. So I can have a look at the columns underneath and so on and so forth, right? So I'm going to create my external reference. Let me do this. Made the fonts nice and big so everyone can see that. So over here, I've got HDFS, the IP address, and this is a different machine, obviously, different port, and where my file actually lives. So I go through and create this. And sorry? So right now, I'm pointing to a particular file that I've loaded in. And then, well, it actually puts it in a folder because if you look, this is a logical name. So think of this as a Hadoop file name, but in reality, it's actually a folder. It's a directory. Because when you go into that directory, and I'll show you in a sec, you'll see a number of different files that are in there. If you do ls, -ls, you can see all the different files. And I'll show you that just now. So now I can go into my external tables, hit refresh. Okay, good, I can see it. So this is my table, and this is now, I'm referring to this, for all intents and purposes in the rest of my SQL, this appears like a table. I can't do schema, I can't change the schema of it. I can't add columns, drop columns. Right now, but I can certainly select and I can re-output data back to it. So let's have a look in my Hadoop cluster, kind of what this looks like. So I kind of fire up my name node. And let's go through and browse the file system over here. So I've got Danny T. So it says this is it's a folder, But underneath that, you'll see it's got a number of files. If I go through into here and I have a look from the command line, let's see what I got here. So you have to use this naming convention where you preface everything with Hadoop. So Hadoop starts off this process. So you have a number of different options here. So FS stands for file system. Then LS is the list command. So and I named the folder because I know it's under Danny T. So I'm going to add this to it. Okay, so let's have a look at what we've got here. So this is my actual file name. Now remember, I mean, I don't have that much data here, but if this was lots and lots of data, it would be multiple files across multiple different systems. So normally that's why you call it a file. So this is the actual data that I copied into the Hadoop system. So let's put this on the side. So I've got my my table here, and I can see the columns that I've got. I've defined as varchar, and I can go through and I can run a select on it. There you go. I'm getting the data back. So it's all typed. When it comes back in, it recognizes it as date time. So let me go back to my presentation. Okay. So, go to full screen. So querying non-relational data via T-SQL. So we've created the external table with the delimiter. At this point in time, we only support one type of delimiter. It can be any character or characters that you want, but it can only be one. You can't have a pipe and a comma and different types of delimiters. And right now, we support text files. So in the future, we're looking more broadly at XML and video and audio and things like that. But for right now, we're supporting text files because our customers want to process large amounts of logs. And logs typically are massive text files. So we can select queries. It behaves like a normal table with where clauses. As the data comes in, I want to show you the execution plan in a second of what happens under the covers. We can also join it to other HDFS sources, and I can have, in fact, join it to make a join between one HDFS farm over here and another HDFS farm over here, as long as they're both of the same type, either Cloudera or Hortonworks, but not really a mixture of the two. So I can also join data, obviously, between HDFS and PDW, and either store that data back in PDW or throw away that data or basically store that back in HDFS. Very simply like that. So querying non-relational data with HDFS, the data gets imported and moved on the fly. So we have Q tables. We bring in the data from Hadoop. We perform the query within Parallel Data Warehouse and send the results back. Any external data or any remaining data temp tables is automatically cleaned up. So we go over the HDFS bridge in this case. We have the DMS readers. We fire off multiple reader threads, and we read the data into PDW. So in this case, from the distributed SQL plan that we've gone to the control node. We've got the metadata of where the external table, the external file is. We've got that reference. We then inject the execution plan to the various PDW compute nodes, and each one of those goes through, connects to PDW, connects to Hadoop, and grabs the data. So this is parallel now import of HDFS data and export back into HDFS. So this is, again, fully parallelized to be able to do parallel import from HDFS. So I'm using a new syntax called CTAS, which stands for Create Table as Select. So I'm creating a table, click Stream PDW, and note here I'm specifying the distribution of a particular column, and ideally this distribution would be a nicely balanced distribution, so you can have even distribution of data between all of the parallel PDW compute nodes. Then I have a select statement that grabs the data from clickstream. And clickstream is the external table reference that I made before. So again, a HDFS bridge kicks in, grabs the data in a parallel multi-threaded way from HDFS to parallel data warehouse. CETAS, and I'm sorry for these slightly different terms here, CTAS, CETAS, there's also CRTAS, but essentially it's the same thing. In this case, we're going parallel data export from PDW back into HDFS. So in this case, it's create an external table, give it a location, and now I am selecting the data from parallel data warehouse after I've processed it, joined it, did whatever I need to do with it. And now I'm creating the files and the folders under the covers. So you still use one logical name. So the logical name for this file would essentially be clickstream, and the output folder would be the name of the file as far as Hadoop is concerned from a logical perspective. But the underlying files, the text files themselves, have a totally different naming structure. And that naming structure is known by the name node on the HDFS side. So retrieval of the PDW data, again, we spin up multiple writer threads, and we go through and we write the data back into HDFS, parallel writes. So from a functional behavior, what happens if we have an error? You know, we've got a network problem or something like that. So we do a one-time cleanup. The first thing we do is we determine, do we have permissions to that folder? Does the folder exist? Do we have to create it? If there's an issue, how do we clean up after ourselves? Because you don't want to leave, hundreds of little files all over the place. It becomes a real nightmare. And also, to make it easy to determine what files come from PDW, what files you've loaded in, if you wanted to go to the individual Linux file systems and check it out there, we preface everything with the query ID, the year, month, and day, right down to the file index so that you can know what files comprise in HDFS into one logical file. Remember, these are all cut up into up to 64 megabyte chunks. So you load a terabyte of data in there, you're going to have many, hundreds of little 64 megabyte chunk files. So this is round tripping. This is where we, in one query, one SQL statement, bring in data from Hadoop, process it within PDW to join it, or create aggregations, do whatever you need to do with it, and then re-output that data. What does this achieve? A lot of customers want to have their taxonomies on their normal data warehouse solution. The data warehouse solution, your single source of truth, has all of your dimension tables, your taxonomies. It's already managed. This way, you make a link to Hadoop. In one query, you've already matched up. You don't have to have a second copy of all of your taxonomies and dimension tables across in the Hadoop world. And then you can spit the data back out again if you wish. And you don't double up on storage either. The data is actually stored in one location. You can definitely make copies of it if you want, but you only need to really have one copy of it. So let's have a look at a demo, the rest of the demo here. So I ran my query. So I got my data back. That's fine. So I'm sorry, the queries here are overly simplistic. The point here is not to sit here and impress you with how many large SQL statements we can put together, but to kind of show you how it works. I'm sure you can come up with a lot more complicated SQL statements, okay? So now we want to apply a where clause. This is the HTTP, and I preface everything that comes from Hadoop, just so we know what it looks like, with HTTP, and everything from PDW is a normal kind of table. So I run my select query here, and there we go. I ran a function on top of this to get the total call seconds. So I'm simulating here call detailed records from the various providers. So you have the source phone number, the destination phone number, the start time, the end time, but you don't really calculate the number of seconds of the call until you do some post-processing on it. So this would be the post-processing. So when we're bringing in data from an external source, we really don't know the distribution of that data, right? So I want to now show you the DSQL plan that I'm talking about before, the overarching distributed SQL plan and what happens on the covers. So we do that by putting explain under just before our query. We execute the query, and we get an XML output, okay? It's not a nice pretty graph and pictures like it is on normal SQL Server. We're working on it. But in this case here, you do see what happens under the covers. We've got a select from, this is our normal submitted SQL statement, the total cost from the optimizer. And one thing I do want to show you is that because we don't know the distribution, we assume that it's an external round robin. So we take the first chunk of rows, put it to the first node. Second chunk of rows, second node, and we round robin until all the data is essentially brought in. So this is a distributed execution plan. Now normally when you execute a really complex query involving multiple shuffle moves and partition moves, this would be running into the multiple pages. But you can get a very, very detailed explanation about what happens under the covers. Okay, so now we want to go through and import some data into PDW. So I am creating a table called PDW import call logs. And remember, I'm giving it a clustered column store. So, and creating this, and I'm also putting the function here. So I am now bringing in data from Hadoop into Parallel Data Warehouse, doing all my joins. So let me go through and refresh my little table list here. There we go. And now you can see the difference. This is a distributed table because the icon is a little bit different. And this is a replicated table between the two systems, right? Within PDW. Again, you make the determination whether it's replicated or distributed. So now importing data from Hadoop, join it to a reference tables within PDW. So everybody can see it. Sorry if the fonts are a little bit too big. I can make them a little bit smaller. There we go. And re-export it to Hadoop. So I'm doing create external table, telling the system where the data is going to reside, and as select. So I'm getting just the data from New South Wales, and I'm re-outputting it, processing it, re-outputting it back into HDFS. So I'm executing this. And I've got all the data back into the system. So I can now have a look at my link, created a link for me called HTTP output call logs. And I can now go through and select that if I wish. So just to prove that the data is there. So I've linked it to the customer. I now have the customer name, the postcode, the state, the call seconds. So now I can go through if I want to. I've got the address. I can create bills and go from there very, very simply. So all of this, I also want to show you some details about how would we do this in connectivity between other tools like Power View and Power Pivot. So let me go into here. So let's open up a spreadsheet. Blank workbook. So I'm connecting via VPN over to where the appliance is. So hopefully the demo gods are good and the network's not going to die, because it was quite challenging earlier in the day. So I was biting my nails whether it was going to work or not. So okay, so I go in through here and select the cell, say Power Pivot, Manage. Okay, I want to get data from SQL Server. Remembering I'm using a different port now. So it pays if you get the port number and the IP address correct. SQL Server authentication. Okay, let's test the connection. Yay, it worked. Okay, pick my database. Next. I can either write a query, but this is normal, Power Pivot. You can play with that. And I have my tables. So I want to import, say, my customer table, and I want to import my Hadoop table, my output call record table. So I'm importing this data across. Click Close, and there you go. Now I've got all my data into Power Pivot, and I can play with this data to my heart's content and have lots of fun and striping it, creating Power Map or Power Query or Power Pivot outputs and kind of generate the output. So let me go back into my presentation. Okay. So how do you set up Polybase? So if you're going to set up Polybase on the appliance, obviously we would go through and help you. We need to download the Java runtime, and we can't include that. We really love to include the Java runtime in the appliance, but due to certain contractual obligations that we have with Oracle, we can't really do that. We're working with Oracle to be able to do that. So we download the JRE, a specific version of the JRE, very, very simply, install that, and then run an spconfigure, and we specify the type of Hadoop cluster that we have, that we want to work with, either 1 for HDP on Windows, or 2 for HDP on Linux, or 3 for Cloudera. It's that simple. From that point on, we start running CETAS commands, CTAS commands, and being able to manage our data really, really seamlessly, as if it's normal SQL Server or PDW data within the environment. So at this stage, I think we're done with the presentation. I'd like to take some questions if you have any, and I thank you very much for coming and attending this session. Thank you.